So last time we talked a little bit about the on-policy methods, so policy gradient and plus, right? And today we're going to cover off-policy methods, so Q-learning, actor, critic, right? And yeah, so in our roadmap, we're going to cover the second box, right? But before we get there, one thing we didn't cover a little bit was the frontiers of policy gradient methods. So like, what is open? What should we look at? Which things are of practical interest, right? So I thought I'd at least talk about them a little bit and problems that I find interesting, obviously biased by my own interest. But I think I also don't take the pictures too seriously. You can go over the slides later. There's some papers that you might find interesting. But just I wanted to give a high-level overview of the directions I think are interesting to do research on in this space. So I think convergence guarantees, better infrastructure for asynchronous parallel methods, better methods for variance reduction, learning from high-dimensional inputs like images or point clouds, bootstrapping from prior data, and trying to do like multi-agent things, right? Those are like 6 directions I think are interesting, and we'll go over them briefly. But I recommend going through the slides for more detailed references and so on if you're interested. Right, so the first direction is convergence for policy gradient. I think people have looked at it in the LQR, LQG case and have talked about global convergence, and they haven't really looked at it in cases beyond that. And so I think open area of research is proving convergence for policy gradient and trying to see how that connects to practice. And so we had the discussion about the paper last time where we show that the practice and theory deviate often. And these are just a bunch of papers that kind of look at how this happens in different scenarios, how different architecture choices affect it, different training tricks, and so on, right? So I think that's very much an open area of research for empiricists and theorists. The second thing is we talked about sampling is super important for policy gradient. And so a lot of methods that work do this kind of thing where they just scale up massively. And so building infrastructure where you can like parallelize sampling, gradient updates across many actors across a cluster often work really well. And so like with ISIC-GIM and new developments in simulation, a lot of these things work better, but they're not quite perfect yet. So looking into this kind of thing, I think is still open and interesting. We talked a little bit about variance reduction methods. There's some methods like backprop through the void, which we talked about last time. There's other methods that use factorization of the action space to get better variance reduction. But variance reduction is still an interesting area. I don't think our variance is that low. I think learning from images is still very difficult. So if you train PPO from images, you can eventually get it to work, but it takes 10 million samples. And so what people often do in practice for these kinds of problems is that they do student-teacher training, where they would train a student with privileged information and use it to supervise a teacher with privileged information, use it to supervise a student. The like supervision is just supervised learning. And so it's hard to do policy grade directly on images. And so you have to do tricks like that. But it's not really clear how to do that under partial observability. It's not really clear what the guarantees are in that scenario. And so trying to get these things to work from high-dimensional observations is still very difficult. So that's open and interesting. Bootstrapping from prior data, so like doing off-policy gradient methods, or things where you like have demonstrations or offline data and trying to bootstrap from them to get better. So offline pre-training, online fine-tuning, still I guess, poorly understood in practical settings, and you just like pray for the best. And I think we shouldn't have to do that. And so I think that's interesting. And we have a lecture about it later, but yeah, interesting. And lastly, I think multi-agent policy gradient is still like difficult. It's non-stationary because you have many agents. Data efficiency blows up. Learning how to communicate is difficult. So there's like interesting lines of work on how do you get multi-agent policy gradient methods to work, how do you get them to learn how to communicate, et cetera, et cetera. So I think multi-agent policy gradient is still very new. Yeah, so those are like frontiers. I didn't give any details, but there's some interesting papers here that you should look into. And so for projects, these might provide some interesting direction. Questions?
What do you mean by non-space methodology?
Oh, it's like normally in RL, like the dynamics of the environment are the same. The transition dynamics are the same distribution. But if the policies of other agents are changing, then the environment is non-stationary. Okay, now we talked about there's a class on deep robotic learning. So is it useful for robotics at all? So you can train policy gain methods on real systems. And so this is John Peters has some stuff on table tennis from early 2000s. And there's some stuff we did with training dexterous hands with PRPO on a real system. People have done door opening with policy gain-ish methods. And it kind of work, right? But it takes like 10 hours to do a really simple task. And if you increase the workspace, it doesn't work. If you don't have dense reward, it doesn't work. So it's not super practical to train these things in the real world. So I wouldn't, if you were to train robots in the real world, I wouldn't recommend policy gradient. I think what works a lot better is these methods which train in simulation transfer to the real world. So you have these like wildly parallelized simulations. This is from ETH. I think this is some stuff from NVIDIA, right? And so they train on wildly parallelized simulations and then use like mild amounts of adaptation to adapt to the real world. And even though like I think the locomotion stuff is actually pretty amazing, but manipulation is still very restricted settings, very similar train and test domain. Still not quite solved for manipulation, but I think locomotion, that's pretty promising approach. And PPO seems to work best in those cases. Cool. So we'll talk about this in more detail in the sim to real lecture. But I would use, if you were to use PPO or policy gradient, use it in simulation. Cool. So very quickly, pros and cons. I think policy gradient is nice because it's super simple. We've like figured out the training tricks that make it stable. So you almost always have good asymptotic performance with enough sampling. It's easily compatible with deep models, right? You can use like your fanciest architectures and it seems to work. And you often don't have to worry about contact modeling and those kinds of things. So it makes it easy to train. The challenge is that it's so sample efficient, it becomes impractical in some cases. It's fully on policy, the data efficiency is horrible, and it's when it doesn't work, it's like, right? It's like hard to know why it doesn't work because it's very black box, right? So yeah, I would use it for games and simulated characters, but not for robotics unless you're doing sim to real. Does that make sense? Any questions, opinions, concerns, thoughts? No? Does anyone use policy gradient ever for anything? Does it work?
Yeah, I use for ping pong training.
Ping pong training. Does it work?
Yeah, but compared to the other ones like cross entropy, its performance is poor.
Oh, really?
Yeah.
I see. I guess cross entropy is even dumber than policy gradient.
But like the learning is faster.
Right.
Yeah.
Do you have a sense for why that is?
So, I mean,
is it the parameterization in?
So, like models will depend on the feature and traffic.
I see.
So, if we design properly for cross entropy, then the learning would be like even within 2 hours or 3 hours.
I see.
Okay. But it's definitely better than DQN, I think.
Better than DQN?
Yeah.
How come? Like as in terms of convergence and so on? Or?
Yeah, in terms of learning time.
In terms of learning time?
Yeah.
Okay. That's surprising. Yeah, I'd be curious to hear more about your experience. Right. So today what we're going to talk about is trying to go from on-policy methods to more off-policy methods, right? How do we build methods that we can use to train robots with directly in the real world, right? So we're going to describe how we go from policy gradient to actor critic to Q learning, right? And then we're going to talk about how do we make these methods work in practice? So what are the tricks that you need to get them to like even learn anything on domains of interest, right? In robotics. Then we'll talk about how do we get them to match PPO and like the best on-policy methods in terms of their asymptotic performance. So if you let it train for a while, at least it should be as good as the other methods. And so we need some more changes to get there. And then we'll talk about some challenges, like what makes it, what makes it difficult, briefly, right? And we'll leave open problems for next lecture. Right? Does that structure make sense? Cool. Okay, we're going to go much slower because I think the first lecture was too fast. So we may not finish. It's fine. We'll use the next lecture. Right. If you have any questions, stop me. It's fine. Yeah. Please don't sit here and not understand. Right. All right. So the first question we want to ask is, what can we do to make policy gradient more suitable for robotics? Right. And if you look at the policy gradient estimator, right? The challenges here is that it's on policy. You can only use your most recent batch of data, which makes it super data inefficient. And it's still high variance, right? So high variance means you need to sample more. Sample more means it becomes impractical to run 10 million samples on your robot. And so the question we want to ask is, can we develop a low variance off policy RL algorithm that we can use to bootstrap from prior data? I just mean data to all prior iterations, so it's off policy, while being able to learn in the real world. Okay, so if you look at your policy gradient estimator, the challenge was that we're using a single sample estimate, right? So every time you're getting your sum of rewards, you're using just the rewards in that single trajectory. And so it's a single sample estimate. And we talked about last time what we really want, something that looks more like this, right? Some like average return to go, right? The problem is that in any continuous space, right, the likelihood of returning to the same state is very, very small, right? And so you don't even know how to group states together to get this average return to go. Right? And so what we're going to use is we're going to use the magic of function approximation, right? So we're going to say that, okay, maybe we'll never get back to the same state, right? But we'll get back to states that are close enough, right? And if we can bundle the estimates from states that are close enough, then you can get a lower variance estimate, right? So what function approximation does is it says, okay, it gives us a way to like share information between these 3 points, which are like roughly similar, right? So if we represent our, if we try to use a learning method to represent this return to go, then you can bundle the estimates across, similar states and so lower variance because you effectively have more samples, right? So the idea is that if we were just doing policy gradient, we only use one trajectory to get a single sample estimate. If you're using function approximation, you can leverage information from similar states in other trajectories. We'll introduce this notation of Q functions, right? And so what I mean by a Q function is it's going to be an estimate of this return to go, right? So we're going to denote the Q function Q5 ST80 as the expected sum of rewards in the future. If you took ST now, if you're at ST, you took 80 for the first step, and then you follow the policy phi thereafter. Right? And so it's essentially estimating exactly what we want here, right? We're trying to say we want to estimate the expected sum of rewards in the future. If you're at S, you took A, and then you acted according to your policy thereafter, right? And so what we're going to do is we're going to introduce this notion of a Q function, right? It's just telling you how good is a particular action A at some state S if you follow the policy phi thereafter, right? Yeah.
Is phi here a deterministic policy?
It can be a stochastic policy. Yeah. It's expectation. And then our Q function is we're going to substitute our Q function into policy gradient to like make it lower variance and better and so on. So the Q function does what I was saying with function approximation. It bundles your estimate across different S and A. And so we're going to represent our Q function with some deep neural network or function approximator. Right? That's what's going to let us lower the variance. Make sense? Right? Okay, so how do we estimate a Q function, right? A Q function is just expected sum of rewards in the future at some state S and state S action A. the first thing you can do is you can just do Monte Carlo estimation. Right? So imagine you had a bunch of samples from your policy, right? You could just do regression from state and action to the sum of rewards in the future, right? You can just take all your trajectories, compute the reward in the future in that trajectory, right? And then you can just like do simple regression from S and A to the reward to go. And so the only difference from policy gradient is that we're representing in policy gradient, we're using literally the sum of rewards. Here we're going to just, we're going to use function approximator to regress from state and action to the sum of rewards and use the function approximator instead of literally the sum of rewards, right? Fairly simple. And so the first thing we can do is just literally Monte Carlo regression. Now, this is obviously not what we're going to do. And why? Well, one is that it's unbiased as an estimator for sum of rewards, but it's high variance because you're still computing the sum of rewards across the whole trajectory, right? And so you might need a ton of samples to estimate that Q function well. And secondly, it's not off policy, right? Because you need to sample from pi in order to compute Q pi. It's not off policy. And so it doesn't really satisfy the criteria that we want, right? Make sense? So in general, when you're implementing these algorithms and trying things, if you have enough samples, Monte Carlo Q will almost always work. So you should just use this as a sanity check, right? The Q function is now working, it's divergent, blah, blah, blah. Just like do Monte Carlo regression on your Q function with a ton of samples, and you can use it as a like metric to check things. Just a pro tip. Okay, so what we want to do is substitute the sum of rewards in policy gradient with this Q function, right? But and we want to do it in a way that lowers variance when we estimate it well, but we want to do it off policy, and we want to leverage some more structure to make this estimation work better, right? Than Monte Carlo regression. So does the premise make sense? Before we get into the methods. So we had policy gradient. We said, okay, we're going to replace the function approximation. First idea was Monte Carlo regression. Bad because still high variance. We're going to use dynamic programming or methods like that in order to estimate Q pi, right? And that's going to make everything better. Yes? Okay, so the thing to notice, my notation is going to be a little bit sloppy, but it's just for sake of simplicity. But the thing to notice in the Q function, right, is that under the Markov property, it has special structure that you can exploit, right? So you can say that the Q function is the expected sum of rewards in the future. When you start at ST, take AT and act according to the policy path, right? Now you can decompose that into the sum of rewards at the first step, right? Plus the sum of rewards at every future step, right? And now if you look at the second term, it essentially looks like a Q function again, right? And so you can write this as a recursive, there's a recursion you can write, right? Or dynamic programming, where you say that Q pi is the sum of rewards SDAT plus an expectation over the next state sample from the dynamics given SDAT, and the next action sample from your policy given ST plus 1, right? And so this just holds by literally decomposing the Q function and plugging in the definition of the Q function, right? Nothing fancy, no tricks. So yeah, I have a question. Okay, so yeah, this is what you call the Feldman equation, right? Super easy. When you're like, this just holds for all Q pi's. Right? If you have a Q pi, we're not talking about how to estimate it yet. I'm just saying that if you had a Q pi, this would hold. Right? And what we're going to do is we're going to go from this Feldman equation to an objective that you can use for estimation. Does that make sense? Right. So all we're doing is essentially intuitively, you can think of it as dynamic programming, right? So you're saying that at SDAT, you're going to take the current reward plus the Q function of the next step, and then the next step, and the next step, right? And so it's dynamic programming, propagating values from the end back to a particular state just by like recursing the values. Right? The interesting thing here which is going to be great. So okay, what special structure did we leverage? The first thing we leveraged was the Markovian property, right? The fact that we didn't have to like consider all the previous states before. You can only get the Q function at st plus 1, right? You're good. And then the second thing is that this is going to allow us to actually, this is true even if AT is coming from a different policy than pi theta, right? And so this is true because you're allowing this action to be any action, right? This thing is true even if like AT has really low likelihood under pi theta, right? And so the important bit, that's going to be the important bit to allow it to be off policy, right? We're going to say that this thing holds no matter where AT comes from, and it's using the Markovian property, which is allowing you to decompose things step by step, like into one-step dynamic programming, right? Right. So those are the two important things which is going to let us like estimate things better. Make sense? Right. So how do we go from here to like a method that we'd use in practice, right? So given the Bellman equation, what we're going to try and do is we're going to represent the Q function by a function approximator, right? Something that goes from state action to reward to go, right? And we're going to use the same function approximator on the right and the left, right? It's just you're going to stick in st plus 1, at plus 1. Oh, no, there's a typo. St plus 1, at plus 1 on the right, and you're going to stick in st and at on the left, right? But that still is not an objective, right? So how do we turn this into an objective? Well, we can say that let's parameterize our Q function by phi, right? You want your Q function to be pretty similar to the true reward R SDAT plus the expected Q function at some next state ST plus 1, given an action AT plus 1 that you sample from your policy pi theta, right? So what you want to do is you want to make these things as similar as possible, right? And so you can formulate an objective where you say, okay, given some bucket of data, right, D, let's call it D for now, right? You're going to sample tuples of transitions, ST, AT, ST plus 1. And you're going to say, hey, the Q function SDAT should be as similar as possible to our SDAT plus the expected Q function at the next state, ST plus 1, right? Now, there's a few things that are, we made some jumps here. So let's go through those, right? The first thing is we're going to represent both of these by the same function approximator, but you notice I put a hat here, right? So what we're going to do is we're not actually going to allow the gradient to flow through the right-hand side, right? And so you write up the gradient of this thing, you only take it with respect to phi, and you don't take the gradient with respect to phi hat, right? Our phi hat is not a function of phi, basically. Right, so you'll have the same, they'll have the same value, but you just stop the gradient through phi hat, right? And there's like a lot of research in this area. Like naturally, you think, okay, like when you have the Bellman equation, you'd want to just minimize the Bellman error, right? Because you know that it converges the Bellman error holds. But in practice, if you do that, it doesn't work so well. It's biased. There's a bunch of other issues with it, right? So usually, what you do is you stop the gradients with this guy, you only take the gradients with the left-hand guy, right? But every time you take a gradient step, you just like, these two have the same value, it's just that you stop the gradient with the right-hand side. And so this is not actually gradient descent on like a well-formed, it's not a gradient descent on the Bellman error, because gradient descent on the Bellman error would go through both sides, right? That's something you call Bellman residual minimization, right? But that doesn't work as well. No one uses it in practice. And you can think of this as it's like a different procedure, which is essentially fixed point iteration. Right? It's not gradient descent, it's like a different procedure. And that's, there's a bunch of theory work and practice work on how to get fixed point iteration to converge. But what we do in practice is not, like the way you implement it looks like gradient descent, but the important bit is that you're not letting the gradient go through the right-hand side. Right? Yeah.
When do you update phi hat? At the end of the data set or at the end of the semester?
Right. So one thing you could do is you could keep phi hat fixed for many gradient steps. And then after you've done a bunch of gradient steps, then you copy phi into phi hat. I'll talk about what we do in practice a little bit later. Yeah, but the first version of this kind of thing was called fitted Q iteration, where you would do a bunch of gradient steps on phi, keeping phi hat constant, and then like copy over phi into phi hat, right? And then replace. Okay, does this make sense as an object? Yeah.
So are you creating the objective function just to make it convex, or does it work even if you apply the modulus?
Well, if you don't do that, then it could just become unboundedly negative, right? You're just trying to make these two things similar, right? I guess you have to make, like, they have to be similar in squared error, right? Not in, like, you could use L1 error if you want, but you can't just have A minus B, then B would just become super, right? There's other, like, more modern research stuff uses things besides the squared error, and sometimes it works better, but like most people use the squared error. Yeah.
So for the Q function, you have y learning, and for the policy part, you have C part. How to learn the two functions together? Is that
Yes.
by one or
Next slide. Yes, I will talk about it in the next slide. Yeah. So this is just phi learning. I'm going to discuss theta learning next. Okay. Any other questions? Cool. All right. So main thing in off policy methods is we're using dynamic programming. We're going to formulate this objective of the Bellman error, and then we're going to try and minimize the Bellman error with gradient descent, making sure we stop the gradient to the right hand side, and that's going to let us learn our Q function, right? And then once we have our Q function, then we can go back to the original thing we want to do, which is improve policy gradient, right? So if we go back to policy gradient, we can say all we want to do now is, rather than maximizing the sum of rewards, we want to maximize the Q function, because the Q function is like the sum of rewards, right? So you're going to say, let's say sample S from your data set, actions from your policy, and you want to choose actions which maximize the Q function, right? And so this is what you'd call policy improvement. You'd call this previous step of getting Q pi to be policy evaluation, because you're evaluating how good a policy pi is, right? And then the next step is policy improvement, because you're saying, I want to make pi better, right? That's what policy gradient would do. You're just replacing sum of rewards with Q, right? So all you're saying is that you replace the Monte Carlo sum of rewards from lecture 2 with the Q function, right? And everything else is the same. Yeah, and this is policy improvement because you're trying to maximize with respect to theta. The previous thing was trying to like do policy evaluation, because it's trying to find the Q pi, which tells you like how good an action is at some state S for some particular policy pi. Yeah. Okay. Right. And so the nice thing is, if we estimate Q well and it bundles things appropriately with functional approximation, then you should have a lot lower variance. You should be able to train Q pi off policy. You should be able to use all your prior data. And so you should be able to do a lot better than policy gradient, right? Because we've got both of our criteria. We're off policy, we're lower variance, and now we just stuck this into policy gradient with the off policy lower variance estimator for the sum of rewards. And so we should be good. Yeah. We won't be good. And that's why we have, the whole lecture. But in principle, we should be good. Okay. So how do we actually do this update, right? Just really quickly, there's a policy improvement update, right? We want to find the policy which maximizes the Q function. You can use reinforce from the first lecture or the second lecture, right? You can use grand log pi times Q. You just replace sum of rewards with Q. Or, as we covered in the discussion section, you can use reparameterization, right? It's difficult to use reparameterization in like regular policy grid, because you don't know the dynamics of the environment, right? But if the Q function is differentiable, which it almost always is, and you can reparameterize your policy, right? By reparameterize, I mean you can take gradients through sampling, right? Then you can do your policy improvement step with reparameterization, which is a lot lower variance, right? And so when you do policy improvement, You can either do likelihood ratio, which is easier to apply to a broad class, right? You can use it for whatever, or you can do reparameterization, which is lower variance, often works way, way better in practice. Right. So if you look at the homework, you'll try policy gradient, it won't work. You try reparameterization, it'll work better. Right. Any questions? So remember lecture 2 and the discussion. Right? So I would encourage you to go back to Backprops with the Void. It has a good discussion of reparameterization. But the point is, when you pass the gradient through here, if you know how to, you know the policy that Gaussian or some function that you can reparameterize, then you can pass the gradients through and you have a better estimate. Yes? Okay. So if we try to summarize what we've talked about, right? The procedure now is going to look like this. We collect some data, right? Then we say, we're going to minimize the Bellman error, right? In order to learn the Q function, which we'll often call the critic, right? And so you like minimize the Bellman error as we discussed earlier. And once we have the Bellman error minimized, we try to do policy improvement. So you try to improve the policy, or what we call the actor, right? We're using either of those two gradients we talked about just now. And then you go back, collect some more data, and repeat, right? So policy gradient, collected data, gradient step on pi, collected data, gradient step on pi. We're just going to add one more step in between, which is learning the Q function by minimizing the Bellman error, right? And so the good part about this is that it's lower variance, it's all policy. It's much more practical to use for robotics. Right? So does active critic work? Sometimes. So this is a video I had to dig up from Jan Peters, many years ago. Oh shit, that's 20 years ago. But it's like trying to hit this this ball bat using essentially something very similar to what we just discussed. But it's like a very, very restricted action space, very small state space, there's all these tricks. So it works kind of. Yeah, that's what Jan Peter said. It's too slow for real robots, right? So I think we need to make some more tricks to make it work on the tasks we care about. Vanilla, this is not going to work, right? Right. So we talked about conceptually how to go from policy gradient to actor gradient. And let's think about, okay, what do we need to make it work with deep networks, on problems of interest, stochastic optimization, so on. So what can we do to make all policy algorithms work in practice, right? The first thing we want to do is we want to go from these batch updates. So I was saying we could take many gradient steps on phi and then swap out phi to phi bar, like I was explaining. But instead, what most things do in practice is that they do online updates, right? So every time you take a sample, you also do an update, right? So you want to collect data, learn the Q function, take a gradient step on phi. By update the target, I mean copy phi into phi hat, right? So like the phi on the left side is copied into phi hat, and then you repeat, right? Now you can do this by taking a bunch of data first, and then taking some gradient steps, and then collecting a bunch of data, right? But what you'd want to do in practice often is like take a sample, and then every sample you want to update your policy, right? So it's like more reactive. You get your policy and your Q function changing much more on the fly, right? And so you're gonna take every time you collect a sample, you're gonna take a step on your critic, and you're gonna take a step on your actor, right? So step on your Q function, step on your policy, and then you're going to repeat, right? So it's going to allow for much more immediate updates than having to wait a long time and do a bunch of gradient updates. And so TQN and etc., all of them do this like online update stuff.
When we do grading stuff on the boundary layer, do we use the entire data set or cycles?
It's a good question. Yeah. So I'll talk about it next, but what you typically do is you like would sample a batch from your set of data thus far.
Oh.
Right. But the most naive version would just use the latest sample, but it's high variance then.
For the gradient sophistication, it's like if a batch size of one, so you do one new trajectory and you update both your policy and your.
Not even one new trajectory, one new transition.
Oh,
right. So it's like every time you take a transition, you do an update. And that's what it was. How do you say it?
Again,
Okay. That's what I was saying in terms of like, do you sample a batch? Do you do it on a single sample? And we'll get to that next.
So these are two separate networks.
The Q function and the policy?
Yes.
Yes, the Q function and the policy are separate. The Q function is trying to evaluate the policy and the policy is trying to act in the environment. Right? So they're two different. Okay, so the problem, as you noted, astutely, is that when you're, when you're performing updates online, first thing is that if you just take updates with, you do like online optimization, like every time a sample comes in, you take a gradient step. The updates are super correlated because you're like doing updates with a bunch of samples in a trajectory. So it's not at all IID, right? And secondly, if you're doing this target update all the time, right? Like you're copying phi in the phi hat all the time. It's the right-hand side of your equation is like moving a lot. Right? It's like super unstable, doesn't work in practice. And so when you just try to do this online naively, it's not going to work because of these two issues, right? And so there's some fixes that they proposed, which we'll talk about now, which make this a little easier, right? So the first thing is that you want to decorrelate updates. So you don't want to take gradient steps on samples that are super correlated, right? And so you're going to use kind of naive trick of you're going to have a big reservoir of data. You're going to keep dumping your online samples into that reservoir. You're going to shuffle the reservoir and you're going to sample from that, right? This is what you call a replay buffer, right? And so all you're saying is that take all your experience, stick it into your replay buffer, shuffle up your replay buffer, and whenever you're doing gradient updates, sample batches from your replay buffer. So you're decorrelating the updates closer to IID, and so performs a lot better, right? And so what you'd usually do is use some sort of ring buffer or something like that for your replay buffer. So you maintain some set of data that you've seen thus far and keep purging the replay buffer after it gets full, right? And then every time you get a sample, you stick it in your replay buffer, right? And every time you want to do an update, you shuffle up the replay buffer, you sample from it, and then you do a gradient update on the critic. So this D is just our replay buffer, right? You're just sampling IID from your replay buffer. And then the same thing when you're doing the policy update, you just sample IID from your replay buffer, right? And the nice thing here is that you've now decorrelated your updates because you're not only doing updates on transitions from this trajectory, but on other trajectories too. Yeah.
Why is it that sampling on correlated data is so bad? Because like if you have a weird trajectory, you do that.
Right. You just like you have a weird trajectory, you end up in a part of space. Like mostly when you're doing supervised learning, you want to be IID. All the characters. Okay. Now the question is, okay, how should we sample from the replay buffer? Should we just stick it in there, shuffle it, sample uniformly? Like the trouble might be that a lot of your data is not that informative, and some of your data is super informative, right? And so the most naive strategy is to sample uniformly from your replay buffer, right? Throw it in there, shuffle, sample IID. But there's also a bunch of other ways to do it. So you can prioritize things transitions by which things have the highest development error, right? That's what you call prioritize experience replay. Or you could prioritize by things where this thing has that should be lower. But you should say you can prioritize by things where the targets are accurate. And some of the readings that I've assigned kind of look at different sampling strategies, right? But often in practice, choosing your sampling strategy carefully makes a huge difference in performance. Right, but it's not very clear what the right sampling strategy should be, and so that's very much an open area of research. It's a great project direction. Right, okay, but what do we cover here? We're saying online updates, take all your data into the reservoir, shuffle things up, sample batches when you're doing updates, so decorrelate the updates, right? Okay, so that's the first idea. So going back to our challenges, it deals with this issue of correlated updates, right? Now, the second issue is that if you keep copying the phi into phi hat, like Schmidt was saying, right? Like you copy the phi into the phi bar here, but you keep copying this at every step. It's super unstable, right? And so all you're gonna do is you're gonna just hack it, right? So you're just gonna say, rather than moving pi bar directly to pi, you're gonna move it slowly, right? And so you're just gonna say, rather than saying phi bar is equal to phi, you're just gonna say phi bar is 1 minus tau times phi plus tau times phi bar, right? And so you're gonna, depending on your choice of tau, you're gonna allow it to move slowly or fast, right? And typically you choose a value of tau that's pretty close to 1, so that it like doesn't move that much. It moves kind of slowly. And this is what you'd call a polyadiagram, right? And so the two tricks that the original DQN paper introduced in like 2014 was just Q learning or similar. We'll get to Q learning in a second, but it's basically just doing a replay buffer and then doing a target network. Right? That's it. And then people publish like 20 papers just applying this trick to like 50 different algorithms. And that doesn't work anymore, but it is super helpful. Cool. Right. So if we go back to our like schematic, right? We start by collecting data, you add it to the buffer, right? And then you sample a batch from the buffer, you learn the Q function by taking a gradient step on the Bellman error. You take an update on the policy by taking a gradient step on the policy. Then you update your target with this polyic averaging, with slow update, and then you repeat, right? Now, you don't have to take one gradient step. You can take several gradient steps, but it doesn't always work. Yeah.
Should you be updating after one step in the real world, or like let a trajectory run with the current policy?
What I found to work best is if you just have an asynchronous updater, which is just you're dumping data in the buffer and it's just running all the time. But I think both kind of work. Yeah. All right. So the next question to ask is, okay, there's still a lot of machinery. Like, look at this thing. Like maybe too much machinery for us to be happy, right? So can we simplify? Right. So we have this Critic update, which is doing policy evaluation. It's telling us how good a policy is. And this actor update, which is trying to make the policy better, right? What if we just, is there a way we can just get rid of the actor, right? No actor. What if we instead of having an explicit actor, we just said that the actor is the max of the Q function with respect to A, right? And then directly in the Bellman update, rather than having an expectation according to your policy, right? You just do a max on the second step, right? So what you're trying to do, essentially, this is essentially, you're trying to say that the Q is similar to the R plus the max of the next Q, right? And so you've removed the actor because the actor is now implicit in the Q function, right? So the policy is just saying, if you can compute the action which has the maximum Q value, that's your policy. You don't need a separate network. It's just implicit in the Q function, right? And then all you have to do is when you're doing your Bellman update, just change that expectation to a max, right? Rather than sampling from a particular policy, try to find the max of the Q at the next state. That's it, right? And that is what you call Q learning, right? Or some version of this. The only difference is that you remove the actor and the Q function is implicit, the policy is implicit in the Q function, and you change your Bellman update to have a max rather than expectation. Yeah.
Does it work if like your action space is like Q?
Yeah, we'll cover that. Good question. Yeah. So the scheme would be, you collect your data, you add it to the buffer, you sample a batch from your buffer, you learn the Q function via this modified max Bellman update, right? And then you do the same target update, and then you repeat. But we've, as compared to earlier, we've cut out this actor step altogether, not, right? And so we've like simplified our procedure. Right? You just learn the Q function, less hyperparameters, less things to worry about. And so it's a much simpler procedure. That makes sense, right? So, okay, so that's great. Now, there's a good question about what happens if like your action space is huge, right? So this is easy to do in discrete spaces because you just enumerate act and then you pick the max, right? But in a continuous space, you have to solve that optimization, which is a pain, right? And so there's no like super awesome ways to do it right now, which is why most people would still use the actor critic methods in continuous spaces. So in a discrete space, you almost always use Q-learning rather than actor critic, but in continuous spaces, you still use actor critic. But if you were to do Q-learning in continuous spaces, one idea is to just sample a bunch of A's, like just sample 1,000 A's and pick the max. And it's like biased and you need a lot of A's, but it works well in practice, as I'll show next. Or you can try and structure the Q function so that that maximization is easy. So you can make it convex or quadratic or something where it's very easy to compute the max, right? And so some of the readings that I've assigned do QT-opt, which is sampling based, or normalized advantage function, which is like structuring your Q function in a way that makes it easy to input, right? But no awesome solutions. What people mostly do is actor critic. But in a discrete space, always do Q-learning. It's works way better. Okay. So on videos, using the sampling-based version of Q-learning, this is some stuff from Google, which shows really high success on grasping and picking and placing and rotating and those kinds of things. Just with it, they have like 14 robot arms that run all the time. And yeah, that's all they do. But the interesting thing in their setup is they have a hugely distributed setup, which allows you to do this like sampling-based maximization easily, because you can just sample a ton of A's and take the max, right? So this is one example, and then using actor critic methods is another example from some folks at DeFi, which does these like fine insertion things by training directly in the real world. And so both of these were trained directly in the real world, as opposed to the PPO stuff, which is largely trained in simulation. Now we're at least able to get the training in the real world a bit better, right? It works eventually. Yeah. Cool. All right. So, right. So we talked about how to go from policy grade to actor critic. We talked about how to make things practical with target networks, replay buffers, and removing the actor. Right. Everyone follows? Any questions, opinions, thoughts?
Yeah, and just like one. So when you're like running this Kubernetes things in practice, the sort of like collect data step, you're running sort of, you're choosing the action to be whatever the max is that you're currently with maybe some like epsilon greedy or other people, what usually works in practice.
Right. So in actor critic, you would like do you just sample from your stochastic policy. And in Q-learning, you would do something like epsilon greedy or like some Bozeman noise.
Okay.
Yeah, softmax on the keys. Yeah. I don't think that's the best thing to do. Like probably that you could have a separate exploration policy. That'll probably be a lot better. And there's some things that try to do that, but none of them work. Like nobody uses it.
Because you're saying like when you're doing this like Q-learning thing, like you're going to draw when you sort of, you're basically always just drawing something from the replay buffer and training on that, right? So in some sense, it doesn't really actually matter, you know, how you were sampling. I mean, it does matter, but like
it does matter because it's affecting the replay buffer, but it's lower.
Right.
Yeah. Right. But if you like did some like more recency bias sampling from the replay buffer, it'll probably be better to sample it. Yeah.
You go back to like the correlated or like the decorrelation or like the sampling from the replay buffer randomly, like get rid of decorrelate updates. Is the reason you want decorrelate updates because you don't want like either policy be super like specific? Like what's that?
Yeah, it just becomes like, imagine that you had like one trajectory that was like sampled randomly, but it's like spuriously horrible, right? Like, let's say you took a bunch of gradient updates just on those things. Now your policy and your Q function end up in a part of the space which is like completely not reflective of everything else. And so it's like trash and kind of intuitively. Right? But also your supervised learning problem is not IID anymore. Like, or your this problem, you're not sampling IID data anymore. So it's like not as stable. Yeah.
But how would the 10 arms that Google has make it more like IID if it's like you're sampling like a buffer that has like multiple different arms like working on so it's like different.
Yeah, I think they found that it actually is more robust, shows better generalization, etc. Because when they go from one arm to 14 arms, because each of them are a little bit different. And so yeah, I think it helps. Okay. I have like 20 minutes. So these methods still, when you like, if you just use these tricks, they like don't quite match up to the best tuned PPO implementation. And they're like often unstable and like this was when you know we had most of these is maybe 2017 or something, and it like worked okay, but it just like didn't match PPO, so nobody wanted to use them, right? So how do we make them match the performance of on-policy algorithms, at least in terms of asymptotic, right? So there's a couple of tricks I think made a big difference, or they're not even tricks, methods, right? That made a big difference. And let's go over them briefly. I'm not going to get too into the details here because it's going to take too long, but it's part of the reading, so you should go through, right? So there's two issues that happen often that make these things work poorly, right? The first one is, well, two of many, but the two I found most significant were overestimation, right? So your Q functions often are like way overestimated. So like, let's say your blue was your true Q function. The estimated Q function is way overestimated, even on actions that are not good. And so often your performance is bad because you're overestimating your Q function. I'll talk about what. And the second is that exploration often collapses. And so your policies get stuck and doesn't work that well, right? And so we'll talk about solutions to these two things, right? So the first issue is that, let's say, you know, we look at our Bellman update, right? And let's say we look at the like, max version in Q-learning, right? If you're using function approximation, right? The Q phi hat is not the true Q function. It's like a noisy version of the true Q function. Right? Like sometimes you might overestimate, sometimes you might underestimate. Plus, if you have a stochastic environment, sometimes you overestimate, sometimes you underestimate, right? So while you want that thing to be like the true value, let's say it's unbiased, as in, you know, different batches give you different Q phi hat, and they're zero in expectation, right? But they have some variance. Because of the max operator that you're putting, it's going to try and overestimate, right? So what we're going to say is that if Q phi hat was exactly the right Q, then there would be no overestimation. But because of some function approximation, you're going to have some variance in your estimation of Q phi hat. And then when you take a max on top of something with variance, then you get an overestimate, right? And so here's some blocks of what the true Q function should look like, right? Dotted line, and what the estimated Q function looks like. Look at the orange line, right? Same thing in a different environment. You can see that it's like way overestimated, right? And that leads to like really unstable, poor performance. And the key bit is that you're taking you're doing this expectation over max, right? Where really what you want is a max over expectation, right? And so you're doing the right-hand side thing on individual transitions, which might be, you know, noisy estimates of the true Q function, and you're taking the max over those. Whereas really what you want to do is really what you want to do is take the max of the expected Q values over many different noisy estimates. Right? So here's a illustration, right? So imagine that your noisy estimates of your Q function, some of them overestimated, some of them underestimated, right? And your max, let's say you had two things that you're choosing the max between, right? X1 and X2. Your max with respect to X1 is going to be 4. Your max with respect to X2 is going to be 6. But your expectation of X1 is going to be 1. Expectation of X2 is going to be -1, right? Now, if you look at the max of expectation, right, that's going to be 1. Whereas expectation of max is going to be 5, right? So this is pretty easy to prove, but you can prove that the expectation of max is greater than the max of expectation, right? And so what's going to happen is if you go back to your Q-learning update and those Q5 hats are noisy and you put a max on them, it's going to try and take like the overall, like imagine Q5 hat by chance was like high for some state action pair. It's going to latch onto it, right? Because you're taking the max, and then it's going to propagate some incorrect over optimistic value, right? And so you have this issue where max of expectation is greater than expectation of max, right? And that's what's going to cause this over optimism issue, right? So just to make sure we get it, the issue is Q5 hat is noisy. You're taking max of a noisy thing. You're going to latch on to samples that are spuriously noisy, even if they're not that good, right? And this is what's going to cause your overestimation, right? And this happens when you have function approximation, when you have noisy stochastic environments. It happens in like most things in practice, right? And when you have overestimation, you can have an action that's not so good, have a spuriously high Q value, right? And if you back up the spuriously high Q value, then you're like making the policy go in the wrong direction. Right? And so you have this overestimation problem. Yes.
Is this just like a transient thing? And does it asymptotically go to the same point, or is there?
No, because you're retaining those values. So you have like an optimistic value that you then propagate into another thing, which now has an optimistic value. And so it just like it like stays optimistic.
Compounding.
Yeah. Right. You can see that like it doesn't really like stays optimistic. Right. Okay. So does that make sense? Right. Noisy values because of stochasticity, function approximation, etc. Take the max of noisy value, you get overestimation. If you're able to perfectly compute the expectation before you took the max, then you'll be good. Right? Okay. So that's what happens in Q-learning or in active critic 2. You overestimate when the values are imperfect, even when they're on average, they are correct. Okay, so the solution that I find most compelling is just learning an ensemble of things and then trying to reduce the optimism by taking the min of the ensemble, right? So rather than learning one Q function, right, you learn n Q functions. Each of them have independent updates, right? So they're independently noisy. And then when you're doing the target computation in Q-learning, instead of just using your one Q function, which is potentially, noisily optimistic, you take the min across many different Q functions, right? And so some could be above, some could be below. But the point is that by taking the min, you're avoiding this overestimation, right? So you go back to your previous thing, you're not going to just take each of those, like, let's say one of them chooses, one of your networks has a 4, one of your networks has a 2, one of your networks has a 1, you can take the minimum of them, right? And so that's going to reduce your overestimation because at least you're trying to take the min of all the things. And it does create some underestimation, right? Because you might underestimate things when you're taking the min. But the underestimation doesn't hurt you as much because it just doesn't, those actions don't get chosen. Right? So the important bit is all that you do to change Q-learning is that you learn n different Q functions. And then when you're computing your target updates for Q-learning, you're just going to take the min across n different Q functions. Right? And that creates a huge difference in the behavior because it affects this overestimation problem. Right? So just one change. That's it. Does that make sense? There's other ways to do this. Double Q learning, there's some other techniques that I've assigned in the readings as well, but I find this one to be the easiest and works the best in practice. Yeah, makes sense? Questions? No? Okay. So how well does this work in practice, right? You can see that the lines with the sorry, I'm colorblind, so you have to help whatever the top line is. It improves significantly over, PPO, TRPO, which are on policy, actor, and DDPG, which are actor critic. I guess DDPG, which is actor critic, and actor, which is also policy gradient, and over SAC, which we'll talk about next. But just introducing the TD3 method over here just introduces 2 Q functions. You can also introduce like 10 Q functions, and it works better, right? But yeah, it seems to significantly improve. So that's one thing that allows you to do better than PPO, or at least match it, right? And you can use this in the real world, right? So this is a dog that some folks at Berkeley trained to walk in 20 minutes of real world training time. So they like took it to the hills and then they released it and let it train. And you can drop it in a new terrain and it seems to learn just with 20 minutes of real world training time, just by increasing the number of these Q functions that you learn to affect overestimation and taking more gradient steps. The only change.
Just about 10 minutes.
Yeah, results are pretty good. It does learn to walk in grass and in the office, in dirt, so on. This is one of our videos where we have a hand using similar method, which is trying to, brush this plate, and you can let it train. It trains for a bit longer here, but you can get it to like learn how to do these in-hand manipulation skills just with like letting it train in the real world with this kind of ensemble type method. Okay. Before we get to the last bit, any questions? Okay, so we talked about how to make actor critic methods match PPO. We talked about overestimation bias. Just learn a bunch of Q things, take the minimum. That's it. And the second issue is that often things don't explore enough. Like for instance, let's say you have this ant robot, you really want it to spread out across the whole space, right? But often the exploration gets kind of stuck, or it doesn't explore enough. And so there's a method that try to, or at least when they were first motivated, were trying to increase exploration. And then there's like some more interesting properties about them, which make them better. But the second issue we're going to try and address is how do we deal with insufficient exploration, right? Okay, so often you see deep RL learning curves, right? And they look crazy like this. Huge variance, huge instability. It seems like it's learning something, it drops. It's all over the place, right? And exploration, when you visualize it, like, is very biased. Let's say the goal is here, it's never gonna see it, right? And so, we're trying to come up with a solution to instability and poor exploration, and the solution that was proposed is just adding some entropy into the objective, right? So the objective we've been talking about so far is maximize the sum of rewards or discounted rewards. You just add entropy, right? So you say that you want to do something that's maximum entropy. So you maximize the sum of rewards plus some alpha times the entropy of your policy, right? So it's not just maximizing rewards, it's maximizing rewards plus some measure of policy entropy. And that's going to make everything way better, right? And so it's like a very simple change to the objective, right? And in policy gradient, it's super easy because you just work out the policy gradient theorem. It just adds a small extra term if you just work out J rule, right? So it's like a very simple change to the policy gradient, but it's going to give us a slightly more substantial change in actor critic Q learning, right? We'll go over that next. Yeah.
Do you turn down alpha? Or is it
Yeah. So it's often really difficult to choose alpha. And so what you do typically is you'd say that the entropy is like less or is greater than something. And then you like use dual descent or some constrained optimization to adjust the alpha term. Right. And so that's what works like auto tuning the alpha works best. Right. So when you want to do off policy RL with this entropy added, it's not that trivial, right? I'll have a very short discussion on it, but Sergey Levin at Berkeley has a very extensive tutorial on this, which is really nice. I'll send it out on NetStep, but I'd recommend reading that. Okay, but when you add entropy, your Bellman equation becomes a soft Bellman equation. Right, so your normal Bellman equation, you can write it this way, right? Your Q is your R plus gamma V, where V is your max over Q, right? your policy is just the argmax over the Q. Right? This is using a normal Bellman equation. I've just called B as max Q, right? And when you introduce entropy, you get something really similar, except your maxes become soft maxes, right? And so this is essentially the soft max. Imagine if you took alpha to 0, this would just become the max, right? It's just that it smooths things out. And everything else is kind of the same. So like you could see the V would also become the max Q value if you send alpha to 0 or close to 0. The pi becomes the max Q value if you send alpha to close to 0, right? So it's like essentially just a smoothed out version of the original Q values, but it like allows for more weight placement on like other actions, right? So it's like, since it's smoothed intuitively, it like it allows for exploration to not collapse because it's like placing weight on other actions, right? And if you want to work out how we get to the right-hand side, it's a useful exercise. Just take the definition of the Q function that I've written here and try to plug in, try to expand it the same way we expanded the normal Bellman equation, and just plug in the value of pi into the entropy term, right? And then you should get it, right? So you can write the Q function as the sum of rewards plus entropy. Plug in this definition of pi, and you should be able to like derive this. I'll leave that as an exercise, right? But intuitively, it prevents some premature collapse of exploration. I don't think that's the real reason it works. I think the real reason it works is something that we don't know. So there's even in problems where exploration is not a challenge, it seems to make a big difference. There's some hypotheses that it like smooths out the landscape, or is robust to errors in estimation, etc. But yeah, I don't have a definitive answer on it. But it does help with exploration, definitely, but I think it does more than just that. So again, an open area of research, interesting research question to ask, right? So some demonstrations here of using these maximum entropy things. Some demonstrations with the hand, learning how to do in-hand manipulation, or like rotation of an object or something, learning how to walk, just a few hours of training. Just by adding this entropy term makes things way more practical. Right? And if you look at the like learning curves, just adding entropy, like DD3 to SAC is just adding entropy. It's like a huge gap, right? Which cannot just be exploration for this problem. So I think there's more to it. Okay. So right. So what did we cover? We went from policy grid to critic. We made the tricks to make it work in practice, replay buffers, target networks, Q learning. And then we said, okay, there's still some gap in performance. You deal with overestimation bias and maximum entropy, and then you get things that are as performant, but way more efficient, right? And so then you have algorithms that, as we showed here and in the previous slides, you can actually run. All of these are directly trained on real robots, no simulation, no nothing, right? You just drop the robot in the environment, let it train, and it seems to work reasonably well, right? Okay. I'll cover the last part super briefly. How much time do we have? Like 3 minutes? So off policy algorithms seem like wonderful and way better. So is it just like a silver bullet? And I think the issue is that when they work super well, but then it's hard to get it to work. And on lots of problems, you have this combination of function approximation, bootstrapping or dynamic programming, and off-policy learning, so using prior data. And these three things make it unstable in various problems, right? So, by function approximation, I mean UPy. By bootstrapping, I mean trying to do dynamic programming. And by off-policy, I mean sampling from your replay buffer and not from just your on-policy experience from your current policy. Right? And a combination of these three things make this just like wildly unstable sometimes. Sometimes it works great, sometimes it's wildly unstable. It's not that well understood. And I think, this is what makes it difficult, right? And so some examples here, for instance, are there's a nice paper from some folks at DeFi where they try to study divergence empirically. So they took a bunch of Q-learning runs with all the tricks we talked about, ran it, and 61% of their runs diverged, which is like a crazy number, right? Like the Q function is getting to like 100,000 for something that should be between -100 and 100. Now if you like add in, some of the tricks, like add in target Q, that number goes down. You add in like the overestimation thing, the number goes down. And so there's ways to get the divergence to be lower than 61%, but like on a significant set of environments, it does diverge, and it's not always clear how to make it stable. Right. And so when you have this combination of function approximation, of policy learning and bootstrapping, it gets kind of hairy. Right. I found this example to be super compelling. I think this is from like a old paper from Bertzikis and Cicilis, where they just show that even in the linear function approximation case, no neural net, no nothing, right? Your approximator is linear, and you just run Q-learning on it or anything like that, you get divergence, right? So you get the value function like exploding, right? And I don't think I have time to work it out, but I'll send some notes on it worked out. I think it's interesting, but you can show that even in this like example with two states and linear function approximation, if it's a little bit off policy with bootstrapping and function approximation, it just like explodes. Which suggests that it's not clear how to get it to converge always. Especially in a deep network, it's not always clear. Okay, so I'll send out a note about that. But yeah, things we covered today: policy gradient actor critic, tricks, more tricks, and why it's difficult, right? Yeah, we'll cover open problems and applications next time.